Section 4.3, Graphs of Polynomial Functions. Every polynomial function is continuous. What this means is that they have no jumps, holes, or sharp corners. They could be drawn without lifting your pencil. Every one of them. So all these polynomial functions are going to look something like this. To where there's no holes, there's no sharp corners. What they mean, there's no like V-shaped corners or whatever. The reason for this, look at your normal equations for polynomials, like f of x equals 4x to the third plus 3x squared minus 6x plus 2. A normal polynomial. Is there anywhere that that's undefined? The only places we've talked about so far of being undefined is having zeros on bottoms of fractions. Do you have any fractions there? So could you have zeros on the bottom fractions? No. Square roots, do you have any square roots? So you don't have to worry about square roots being negatives. That's the reason they're continuous. X can be anything you want it to be. The domain is for all the real numbers from negative infinity to positive infinity. That's the reason you have a continuous function. Okay, you can draw it, like I said, without lifting your pencil. When the function does approach, let's see, what the function does as it approaches infinity to the right, negative infinity to the left, is called the function's end behaviors. The following chart describes the end behaviors of different functions. You don't have to memorize the chart, but I do want you to know what's in the chart. I want you to memorize the process of finding it. Here's the easy way. What I mean by even degree and odd degree. Can somebody give me an example of an even degree function? 4x squared. Anything to the second power, fourth power. What about x squared plus 5x plus 6? Would that be an even degree function? Yeah, the degree there is 2. So what we're going to do is, if you look at your chart, all even degree functions does the same thing, and all odd degree functions do the same thing, all depending on what their leading coefficients are. So if you can remember this, x squared, negative x squared, x to the third, and negative x to the third. If you know what those look like, then you know the end behaviors of all these functions. What does x squared look like? Or what's the name of it? Parabola, concave up or down? Concave up. So therefore, think about what that function does. As x approaches negative infinity, you're going this way, right? As x approaches negative infinity, what does the graph do? What does it approach? The graph approaches positive infinity. As x goes to the left, the graph goes up. As x approaches positive infinity, what's the graph approach? Positive infinity as well. So anything that falls into that category is going to do the exact same thing. If you have an even degree with a positive leading coefficient, it increases to the right and to the left, or it approaches positive infinity to the right and to the left. If you have a negative leading coefficient, what does it look like? Same thing, concave down. So as x approaches negative infinity, what does y approach? Negative infinity, it goes down. As x goes to the left, the y goes down. As x goes to the right, approaches positive infinity, the y approaches negative infinity is there also. So even degree, negative leading coefficient, it decreases to the right and to the left. Odd degree, x to the third. You know what it looks like? It's kind of like a sideways S, you're right. Looks like that. Because you got 0, 0, 1 to the third power is 1, 2 to the third power is 8, 3 to the third power is 27. Negative 1 to the third power is negative 1. Does that make sense why it looks like that? So anything that has a positive leading coefficient and has an odd degree is going to have this same end behavior. As x approaches infinity, positive infinity, what does the graph approach? Positive infinity. As x approaches negative infinity, the graph approaches negative infinity. Negative x to the third flips it. So it looks like this. Correct? As x approaches positive infinity, y approaches negative infinity. As x approaches negative infinity, y approaches positive infinity. Makes sense. So anything odd or even is going to follow that same pattern. So if you can memorize those four functions, what they look like, anything that has the same characteristics are going to have the same end behavior. To find intercepts, and what we're doing is you're fixing to be asked to describe graphs. To find the y-intercept, what do? How do you find y-intercepts? You plug in 0 for x. You're doing inverses. To find x-intercepts, you do what? You set y equal to 0. So it says y-intercepts, since we find a y-intercept by plugging in 0 for x. The y-intercept will always be a constant term, or be the constant term. I'll explain more of that later. X-intercepts, the x-intercepts are the zeros of the function. An nth degree function will have at most n x-intercepts. X to the second power will have at most how many? 2. It's quadratic, right? X to the third power will have 3. Because x to the third, that's the basic x to the third. That's x to the third with nothing on it. If you put in like plus 5x squared minus 7x plus 2 or something like that, x to the third looks like this. And it's going to move down to where do you see that you might have 3 x-intercepts? 1, 2, 3. X to the fourth looks like a W. If once you put the other stuff on, if it's just plain old x to the fourth, it's going to look like a parabola. But if you, as soon as you put that other, like x to the third stuff and x squared stuff and x and constant stuff, it could possibly have 1, 2, 3, 4. X to the fourth will. Does it have to? No, because look at this. You're exactly right. If this is x to the fourth, it could have possibly 2, because what if it was lowered down to there? What if you put like a minus 10 on the end of it and you lowered it down? X to the fourth stuff could have 2, might not have any. If this is your x-axis, there it wouldn't have any. It could possibly have just 2. If it had 2 reals, this would be kind of like 2 imaginaries up here. It always has, x to the fourth always has 4 roots. Whether some of them are real, some of them imaginary, or whatever, they'll always have 4 roots. So, back to this. Multiplicity of zeros. In a function, f of x equals this. Let's talk about what your different intercepts are there. X minus 3 squared. Since x minus 3 is a factor, what's going to be a root? X minus 3 is a factor, so therefore what is a root or 0? 3. Since x plus 2 is a factor, what's going to be a root? Negative 2. Since x minus 6 is a factor, 6 is a root. Does that make sense to everybody? Do y'all see that again, the correspondence between factors and roots? This is review, and I like this because it's going over some of the stuff we didn't understand. 3 is a root 2 times. Because this is x minus 3 times x minus 3, so you've actually got 3 being a root twice. And that's what it says. 3 is a root twice. Negative 2 is a root once, and positive 6 is a root 3 times actually. Because you have x minus 6, x minus 6, x minus 6. You have 3 of those. We can also say that 3 is a root with multiplicity 2, and 6 is a root with multiplicity of 3. Look at the graphs though. That same equation, look what happens with the graph. This would be, let's see, a 6th power. This would be a degree 6 polynomial, because this is degree 2 times degree 1 times degree 3. That's all being multiplied together. This is degree 6. So you could possibly have 6 different roots. But some of them are multiples of each other. When looking at a graph, a root with an even multiplicity, this is going to be important too. A root with an even multiplicity, like look back, which one had an even multiplicity? 3, because it had a multiplicity of 2. 3 was a root twice. Look what happens at 3. Bless you. Look what happens at 3. It comes up and it touches it, goes back down. Bless you. Anytime you have a root with an even multiplicity, it's going to touch the x-axis, come back down. Anytime you have an odd multiplicity will cross. Makes sense. So notice you had a root at 6. 6 was a root 3 times. It comes up, does this little funny looking thing here. It actually changes from concave down. You see that it's concave down there to concave up. It's actually an inflection point there, but it's also, since it's a root 3 times, it actually crosses it. Also, negative 2 is a root, and you see that it does cross it there as well. So if you see some inflection happening there, then you know that it's probably going to be a root 3 or 5 or 7 times. If it comes up and touches it but then comes back down, then that's going to be a root twice, 4 times, 6 times. If it crosses it, just goes straight across, root once. Why is that important? Well, I told you the other day I was going to let you cheat a little bit. Instead of plugging in all those values, if you're looking for factors, if you're looking for zeros, instead of plugging them all in, then you can just graph it and look at the graph and tell. But when you look at the graph, just know that if it comes up and it just touches it and then comes back down, that's going to be a root more than once. Does that make sense? So Here you would test 3 twice. So the next part we've already gone over. Local extrema or extremum is your maximums and minimums, and we use our graphic calculator to find that. Later on you'll use calculus to find it. An nth degree polynomial will have at most n minus 1 local extrema. Let's talk about why that's true. X to the third. How many maximums and minimums does that have? Has maximum, minimum, so how many? 2. X to the fourth is your W shape. How many maximums, minimums does it have? 3. Does that make sense what it's saying then? It'll have at most. Does it have to have that many? No. X squared has 1. X to the, let's see, that was to the fourth. X to the fifth would look like that. So you would have 1, 2, 3, 4. So you always have 1 less. Well, come in. I say you always. You don't have to. You can have at most 1 less than whatever that number is. Next up, inflection points, and we've talked about this already. An inflection point is the point at which a graph changes concavity, and we pointed one out. Is this the only inflection point here? No. Can you tell me about what x value there's another one at? Just a guess. About 3. Well, it's not an inflect because it's concave up or concave down this whole time. But notice this graph comes down, comes back up. Do you see it's concave? You don't have the rest of the graph, but it's concave up there, and then it changes to concave down. So somewhere between 2 and 3 is an inflection point. Here you have concave down, and then it changed to concave up, so somewhere around in there's an inflection point. So that's what an inflection point is. You'll learn again how to find inflection points in calculus. Right now we just use our calculators. Odd degree polynomial functions have to have at least 1 inflection point. That's a rule. Not really interested in you knowing that, but they do. Last problem and first problem. Yep. Example 1 says graph each of the following, describe the end behavior, give the x-intercepts, give multiplicity, give the y-intercepts, and the local extrema and the number of inflection points. A lot of information to do on these 3, but some of it's easy. First one, x minus 1 to the third, x plus 1, x minus 1 squared, x minus 2 squared. X-intercepts, y-intercepts, is that the first 2? Or end behavior. Okay. If I multiplied this out, I don't have to. But if I did multiply this out, could you tell me what power my leading coefficient would be? This is x to the third stuff, right? This is x to the first stuff, and this is x squared stuff. So x to the 6th. 3, 1, and 2. My function would be like x to the 6th. Would it be a positive or negative x to the 6th? Positive. It's going to do, to find your end behavior, it's going to do the exact same thing as what would do? What would I call it my model. We had 4 models up here. X to the 2nd, even powers. You got either even or odd powers, and then you got either positives or negatives. So this is going to do the exact same thing as x to the 2nd would. So as x goes to, and I'm just going to draw the ends of it because I don't know what it's going to do in between. But I know at the ends it's going to do exactly what x squared would do. So you can say end behavior, here's how I want you to write it. As x approaches positive infinity, y approaches positive infinity as well. Because as we go to the right, we go up. And as x approaches negative infinity, y approaches positive infinity as well. That's end behavior. Call it EB. Make sense? Now what it does in between, I don't know. Since it's x to the 6th, it might come up, down, and do something like that. I don't know. But it'll have at most 5 minimums and maximums, which is 1, 2, 3, 4, 5. That's at most. It doesn't have to do that, but it might. Next up, it says x and y intercepts. These are easy, okay, especially on this one. How do you find an x-intercept? You plug in 0 for y and you solve it. So 0 equals this stuff here. So what are your x-intercepts? 1. And do this for me. So put in parentheses times 3. X equals -1 and x equals 2 twice. Just put in parentheses so you'll know that it's 2's a root twice. So we're starting to get a better picture of this graph. We know that it's going to cross, and we could do this without graphing now. We know this is going to cross at 1, and it's actually going to cross there. Why is it going to cross and not just go up and touch it? You know that? Odd multiplicity. When it's an odd multiplicity, it's going to go across the x-axis. When it's like -1, it's also going to cross there. But at 2, you see it's a multiple twice. It's simply going to touch it there and then go back up or down or whatever. So we're going to, looks like a parabola. It's going to come down. And it's probably going to do some little, oh, that's at 1. It's going to come down and then back up, and it's probably going to do some funny looking inflection thing there because it does go across it. Then it's going to come down and then go back up. So that's my guess at what this graph would look like. Again, let me explain why I know that. I know that it's going to go up on the extremes because it's like x squared. I know that it's going to cross at -1, and it's not going to do any funny looking something. It's just going to go straight across. I know that at x equals +1, that it's going to look it's going to cross it because it's got an odd power or odd multiplicity. At 2, it's going to come down, simply touch it, and then go back up, and that does support the fact of it increases to the left and to the right. So that's my guess at what it's going to look like, and I'm sure if you graphed it, that's exactly what it would look like. Here's the easier one, well, pretty easy also. How do you find the y-intercept? You plug x in for 0, so you have 0 minus 1 to the third, which is -1 to the third. 0 plus 1 is 1. 0 minus 2 is -2 squared. What is that? Huh? Yeah, should be. If it's a function, because if it had two different y-intercepts, it wouldn't be a function. -4. This is -1 to the third is -1, times 1 is -1, -2 squared is 4. -1 times a +4 is -4. So this is going to cross at, do you see y-intercept is going to cross at -4. So you're getting a good picture of this without having to even use graphing calculator. So it's going to come down a little bit further than what I drew it coming down. I just didn't draw it to scale. My scale is each box counts 2. Okay, so I'm still right on it. Let's see, what else do we have to find? Local extrema, we only have, let's see, and then also the number of inflection points is all we have to do there. So local extrema, we've got a minimum here and a maximum here. Let's graph this thing and see what it looks like and find the extrema. That's the only way that you have right now of finding extrema. So graphing calculator, graph it. So here we go, we see the graph again of this x to the 6 stuff, and it was very similar to the graph that we had here. That's similar. It's similar. It's similar. We had the inflection happening. I do want to see here because I'm not seeing a maximum right there, and I've got a feeling that there's going to be one. But let me change my y's just to see. -5 to +5. Did y'all see it do that right there? I think there's still a maximum or a minimum there. But anyway, if not, let's find the other stuff, and I'm just going to find one of them. You can zoom in. I'm not going to go through the process of finding all of them because it's the same thing. I need to go down a little bit further. Y minimum, let's do -9. Let's see if we can get it then. Because you actually, if you want to find the maximum or minimum, it has to be on the screen, or it won't find it for you. Yeah, I think it is. Like, there we go, that's better. So it's going to be, you can kind of look, it's going to be about -11, maybe -0.7, -11, but the way you find it's the same way you found it for second calc minimum. That minimum's between what two x values? And I mean, you can spread it out. You can do from -3 up to 0. And that's going to find it for you. So you have a minimum at -0.6, -11. and you would just come over to the side, minimum, negative 0.6, negative 11. That's how you find maximums and minimums. I'm not going to go through that whole process again. You can graph on your calculator, and you can use the minimal maximum functions. Where'd the 6 come from? Is the x. See, x is negative 0.6, y is negative 11. So if you actually went negative 0.6 down to negative 11, that's a minimum point. But just that's how you find minimums and maximums. Is that all we're asked to find? Number of inflection points. To find inflection points, simply count where is my graph changing from concave up to concave down, or from concave down to concave up. I think my graph's better, so we're going to use it because you can't see everything on that one. So we have a point of inflection. I'm just going to kind of guess where they're at. We're concave up here, but all of a sudden we're concave down here. So I've got an inflection point about right there. Then we're concave up there, and then we go, concave down there. And then we're going to go concave up somewhere around in there. So how many inflection points do we have? 2. Maybe. So any questions? Okay, on the next one I'm going to do part of it, and I'm not doing all of it. I'm not going to do maximums and minimums. You can do that. You just use your functions. I'm not going to do inflection points. You can pull it up on your graphic calculator, count the inflection points. We'll do the, let's see, in behavior, x-intercepts, y-intercepts, and that's it. Okay? So in behavior, because that's the ones I feel like that you might have most trouble with. This is x squared stuff, this is x squared stuff, so your function is going to be x to the 4th stuff. And again, that's kind of like your model. So x to the 4th stuff, that's an even power. There's a positive number out front because we don't have negatives here. So what's that going to look like? It's going to look like x squared stuff, the in behavior wheel. So it's going to come out here, it's going to go up here, so same thing. As x approaches negative infinity, y approaches positive infinity. Y also approaches positive infinity. There's your in behavior. But again, like Brittany said, in between it's going to look something like probably a W, but I don't know. More than likely. So, next thing, let's find the x-intercepts, y-intercepts. To find the x-intercepts, we plug in 0 for what? Y, good. So x squared plus 3x minus 2. So we have x equals negative 6 with a multiplicity of 2. And we have, okay, what are we going to do with the other? We can try to factor it because we've got to find out, okay, equals 0, solve it and all that good stuff. We could try to full it. Or excuse me, factor it, not full it. We could complete the square, which I don't like completing the square on this one since you have an odd number in the middle. You could try a quadratic formula. But before I do any of that, I'm going to do b squared minus 4ac to see if there's even a solution there. What is b squared? Minus 4 times, what's a times c? Negative 2 times 1, which is negative 2, so 9 plus 8, yeah, we're going to have some answers there. But the stuff under the square root is going to be 17, so obviously this is going to be irrational, the answer is going to be. So x equals, here's your other roots, negative b plus and minus the square root of b squared minus 4ac. We've already done that. Which, see, that's kind of nice to do that beforehand anyway. Go ahead and do b squared minus 4ac. That way you can see, do I even have an answer? And you saved yourself some steps. All over 2a, which is 2. So, do we have any multiplicity of roots there? That's 2 separate roots. You have a plus one and you have a minus one. That's 2 separate roots. There's your 4 roots. You're going to have at most 4. You can't have more than that. So, there's our 4. The y-intercept now. How do you find y-intercept? 0 for x, so y equals 0 plus 6 squared times 0 squared plus 3 times 0 minus 2 is, so 36 times negative 2. Negative 72 is your y-intercept. Any questions? So let's kind of sketch this out and see if we can kind of guess what it's going to look like. We have, let's see, xy axis. We have a double root at, out here at negative 6. I'm just guessing. I'm not counting over. We have, let's see, this would be negative 3. The square root of 17, let's just call that 4. And and that's going to give us a pretty close estimate. Negative 3 plus 4 is 1 over 2, so we have a root at 1/2. So at negative 6, we have a root at 1/2, and this is a double root. And we also have negative 3 minus 4, which is negative 7 over 2, which is negative 3.5. And we know that it's coming this direction and this direction. Since we have a double root here, we know it's going to come down, it's going to touch there. So it's going to look something like that. We know it's going to actually cross here. It's going to, let's see, is that right? It's going to come down, touch at negative 6, correct? It's got to come up. What's throwing me off is it's also got a y-intercept of negative 72, so it should be crossing down here. So what are we missing? Okay, found the mistake. Should have been positive 1/2. Negative 3 plus 4 divided by 2 should have been a positive 1/2 there, so somewhere right in there. So that makes more sense. Because it's going to come down, it's going to touch at like negative 72, that's your y-intercept, then it's going to shoot back up and go up to positive infinity. So instead of a W, it's kind of a warped W. Okay, and that's what happens when you start throwing in all these other terms. It warps it a little bit. But the basic form is a W, but there you go. So last problem, we're finished. X to the 4th, and notice what they've done here. They're not kind. They're not giving you. They're not factoring it out for you. And this is the problem. Watch closely. These are the ones I want you to be able to work. The other ones are great, but these are the important ones. X to the 4th plus 2x to the 3rd minus 10x squared minus x and plus 10. All I'm going to find, again, you can graph that, you can find maximums and minimums, you can find inflection points, those are no problems. That's just your ability to count and use a calculator. So let's see though if we can find out, first off, what's the degree of this? 4, so I didn't mean to do that. You have an even degree again, and you also have a positive out front, it's not a negative, so it's going to be like the W shape. It's x to the 4th is the model, so we know that it's going to be the exact same as x approaches negative, then y approaches positive. X approaches positive, y approaches positive. So the same thing there. Let's see what else. Next, let's find the x-intercepts and the y-intercepts. Y-intercepts easy. Let's do it first. Plug in 0 for your x's and you get 10. Makes sense? Because all this stuff is going to be 0 plus 10. It's going to be 10. X-intercepts is the hard part. And that's the reason we've been going over all this stuff we've been going over. Okay? To find x-intercepts of this, and I'm going to clear this, well no, I'll leave it there. Let me change colors. To find the x-intercepts, we've got to first find out what are possible rational roots. And guys, if you want to, I want you to give me this next step, but then use your calculator and actually find out what the roots are by looking at the calculator, and then test those and show me, hey, I'm just a really good guesser, and it's these 4. But test them and show me. So possible rational roots, I'm going to call them possible rational roots, PRRs, is plus and minus 1, plus and minus 2, plus and minus 5, and plus and minus 10. And again, you'd go through the process, pick one, try it, pick another one, try it. But the easy way is take your graphing calculator and go to y equals, and actually type that in, x to the 4th plus 2x to the 3rd minus 10x squared minus x minus 10x squared minus x plus 10, and delete that last number there. And I still have my graph on what it was a while ago. So do you see that you can do that, and hopefully you can see. Explain to me why I know I don't have my whole graph on the screen. Because it's supposed to go up to the left. So does it make sense that this looks like an x to the 3rd graph, but it's not. This is x to the 4th, so that's another important reason to know the stuff we're doing. This graph's going to come back down, and it's going to go back up somewhere over here. So obviously we have, pretty much I'm saying that this is not a lower bound. You have another root to the left of that, which is obviously probably going to be negative 5 or negative 10. I'm going to guess negative 10. But where does it look like it crosses here? So let's try it. Does that make sense? try -1, and then you never have to go through your whole list again. 1, 2, -10, -1, 10, 1, -1, 1, -1, -11, +11, 10, -10, 0. You've broke it down once. Okay, you've broke it down into, this is x plus 1. It's supposed to be an x plus 1 times this stuff. So this, let's use that ladder method again. Let's try to find something else that works. What else do you think works? Each tick marks 1, right? So what would this be? 2. So try 2, put in a ladder, bring it down, multiply. 3, 6, -5, -10, 0, done. Once you get to this point, this is quadratic, correct? So rewrite it as x plus 1 times x minus 2 times x squared plus 3x minus 5, and then try to factor it there. Because that'll save you a lot of trouble having to try to guess other numbers. Can anybody tell me what the nature of my other two roots are going to be? Are they going to be rational? Are they going to be on this list? No. The only way they're going to be on that list is if that would be factorable, and it's not. If that's not factorable, then you've got irrational roots. If you have irrational roots, we're using either, I don't know, give me some methods. Complete the square quadratic formula, or graphing calculator. You could use your zero function on it. But here we go. Here's our roots. X equals -1 as our first x-intercept. X equals +2 as our second x-intercept. And to find the third one, well, let's make sure it's not imaginary. B squared minus 4ac would be 9 minus 4 times -5, which would be 9 plus 20, which is 29. So we do actually have roots there. So here's your other ones. X equals -b plus and minus the square root of what? Which is, we've already done that, right? +29 over 2. And that would be your other two roots. If you actually work that out, 29, square root of 29 is a little bit bigger than 5. If you want to use 5 as an estimate, -3 plus 5 would be what? Divided by 2 is 1, but it would be a little bit bigger than that, so about 1.1, 1.2. Look at your calculator, right there it is. Your other root would be -3 minus about 5, which is about -8 over 2, which is about -4, but it would be a little bit further over from -4 because 29, so about -4.1, -4.2. And if I change my window, I nearly have it on there. -5, enter. You see at about -4.1 or 2, you have another root. Any questions?